So good morning, everyone. Welcome back to Math 115. Today we're not covering anything new. We're just going to review. So for the review options for the exam, we have our class today. So that's going to be 75 minutes of review, and then there's also going to be my 90-minute office hour session later today. I'm going to reserve a room in LeConte so that we can have lots of people there. So I will also record that session as well and post it to my YouTube channel. So if you weren't aware, I have a YouTube channel and I post all of the lectures. So if you are like, oh crap, I was sick on Tuesday and I missed class, well, you can go watch the recording. It's not a perfect substitute. So generally, I still strongly recommend you to attend class in person every time. I mean, attendance isn't for a grade, so theoretically you could just be watching the YouTube videos, but I guarantee you will not get as much out of watching the YouTube videos as you will sitting in class. But they're there so that if you didn't get something that we talked about in class, okay, you can go back to the lecture and you can hear it again, okay? So that's what they're there for. So announcement-wise, 3.2 homework is going to be due, I think I set it to be due Friday, actually. Due Friday, that's a 3. And exam tomorrow. So the exam is going to be in our usual Wednesday classroom at our usual class time. It'll be basically the same format as the last exam. I put 9 questions on it. And the questions are basically a random sampling of questions which are pulled directly from the homework. Okay, so the questions on the exam are word for word, basically, the questions on the homework, with some minor alterations just to make sure that the numbers work out. So are there any administrative questions before we start in on content for today? Okay, it seems like there are no administrative questions, so I figured what we would do is review. So what we can do for that is basically the following. If you have a topic, just a general topic that you are confused about, then I can give like a short mini guide to that topic, and then we can do a couple example problems. Or if you've been studying and you've been trying some of the homework problems and you came across one that's really annoying you, then we can discuss it in detail. So does anyone have either a topic which they want to discuss or a specific homework problem which they want to see worked out on the board? You got one? Okay, how to do the rational zeros test. Okay. Let's see here. If I go to assignments, maybe we can find a good problem here. Rational zeros test, preview. Where is it? All right, let's try this one. I'm going to write it and then I'll switch the screen. So it's f of x equals x cubed plus 13x squared plus 47x plus 35. Okay. And so the question says find all rational zeros. Okay, so there are basically a few options for what are the zeros of this function going to be, okay? So we have a degree 3 polynomial, so we know that we have at most 3 real zeros, right? But it's possible, let me make this big. But it's possible we have less than that, right? We could have 2 real zeros and 1 imaginary, or we could have like 1 rational zero and 2 real zeros, something like, so let's say if it was like x minus 1, and then we had something like x squared minus 2, right? So if we were able to factor it like this, what would the zeros be? The zeros would be x equals 1 and x equals plus or minus the square root of 2. So these are the type of zeros that will not be revealed by the rational zero test, okay? Because square root of 2 is not a rational number. It is a real number, though. So it's possible we have something like this, or it's possible we have something like x minus 1 and then x squared plus 1, right? If we have x squared plus 1, then this is a situation where we have, okay, so this one is 1 real, 2 imaginary. This one is 1 rational, 2 real. And in fact, really, rational number is a real number, which means that this is 3 real. Okay, so these are the types of situations that we can run into. We can have all of our roots are rational, or we can have some of them are real but not rational, or we can have some of them are imaginary. So those are the options. But the rational root test will reveal to us basically all of the possible zeros which are rational. Okay, so here's how it works. It says the following: if P over Q is a zero of f of x, which f of x, for this to be true, this needs to be a polynomial, okay, if it's a zero of a polynomial. If P over Q is a zero of f of x, then what? Okay, so first of all, let me say, what does it mean for P over Q to be a zero of f of x? It means when I plug it in, what should I get? I should get 0, right? And also, so this is i.e., when we plug it in, we get 0, and also x minus P over Q is a factor. Okay, so these three things mean the same thing. P over Q is a 0, f of P over Q is equal to 0, and x minus P over Q is a factor. They are all three equivalent. It's like saying the same thing in different ways. I was going to say languages, but it's all the same language. So what is true about P over Q? If P over Q is a 0 of a polynomial, so P over Q where P and Q are integers. P and Q are integers. We do this little z with a thing like this. So that's what it means to be a rational number. Then P is a factor of, and Q is a factor of, what? What should go here in my blanks? Can anyone help me? If P over Q is a factor of a polynomial, then the numerator should be a factor of what number? Well, what numbers are going to be relevant in this polynomial for the rational zeros test? 1 and 35. Where do those numbers come from? They come from 35 is the last number, and 1 is the leading coefficient on the first term. Okay, so we know that one of them needs to go here and one of them needs to go here. But it's pretty crucial that we get it right in terms of which number we put on the numerator and which number we put in the denominator. Because if we do the rational zeros test with the wrong number, then, well, we're going to be hosed. So what's really important to remember here is that P should be a factor of A naught, okay? And Q should be a factor of an, which for this example, a naught is 35, and an is actually a3 is 1, right? Okay, so however you want to remember that, you can remember it. One of the things that I was talking about with a student in office hours was just remember P naught, A naught, P naught, A naught, P naught, A naught. Just say that 10 times fast and you'll never forget that P naught goes with A naught. So P is the numerator. It's going to be a factor of the trailing coefficient here, okay? So this 35 here, all right? So that's how you can remember that, and it's kind of crucial that you do, because otherwise the rational zeros test will give you a bunch of candidates that aren't zeros. You'll spend a lot of time plugging in wrong things. Okay, so what are the factors of 35? What numbers can be multiplied together to get 35? 1, 35, and 7 and 5. Okay, so the numerator is one of those, and the denominator should be a factor of 1. What are the factors of 1? 1. Okay, so the set of all rational zeros. Here's the set of all possible rational zeros. How do we get it? We get it by taking any number which is in this set and dividing it by any number which is in this set. Okay? So the first number I could do would be like 1 divided by 1, which would be 1. And also I pick up a plus and minus here. Next up I've got what? 35 divided by 1. That would be plus minus 35. 7, I've got plus minus 7. And then for 5, I've got plus minus 5 divided by 1. Okay, so 5 divided by 1 is just 5. So this is the set of all possible rational zeros. Now there's 8 numbers in this set. We know that they're not all zeros of this function. Why do I know that all 8 of them can't be zeros of this function? Why can't they all be zeros? Yeah, is that what you were going to say, Gavin? Yeah, it's a cubic function, so we can have at most 3 zeros. And there's a set of 8 of them, which means we have some which are no good, right? So we got to figure out which ones are correct. So the way I do that is I just plug in to the function and I check. Remember what we said? If p over q is a 0, then what is true? F of p over q should be equal to 0. So the way I test which ones are zeros is I check, well, if I plug them into the function, do I get 0 or not? Let's try it with, well, if I do it with 1, I'm definitely not going to get 0, right? Because it's all pluses. In fact, if I do it with any positive number, there's no way it's going to be a 0, right? You can see that because this would be a positive number plus another positive number plus another positive number plus another positive number. There's no way we're getting 0 if we plug in something positive. So let's try maybe -1. What would I get then? I would do -1 cubed is -1, and then I would do plus 13 because -1 squared is 1, and then I would do -47, right? And then I would do, no, I wouldn't do minus. Yeah, I would do -47, and then I would do plus 35, right? Okay, so let's see here. We've got we have plus 12, minus 47 is, I think, minus 35 plus 35, right? Is equal to 0. So this was f of -1. Did everyone catch that? Okay, all I did was I took -1 and I plugged it in for x here and here and here. And when I did that, unless I did something wrong, I got 0. So what does that tell me? That tells me that x equals to -1 is a 0. So here's what I could do next. The question says find all rational zeros, okay? From here, there's 2 paths by which you could proceed. The first path would be to say, well, I'm just going to plug in all the other negative numbers and see if I get 0. That's one option. The other option is to say, well, I found one of the zeros, and therefore I found one of the factors, and so I can use long division to divide it out. If I divide out a long division of a linear factor from a cubic polynomial, then I will get a quadratic polynomial, which I can use my regular factoring for. Okay, so that's what I'm going to do, because it allows me to show you how to do long division in the same example. So now what are we going to do? We're going to take x cubed plus 13x squared plus 47x plus 35, and we're going to divide out what? What is the factor? If x equals to -1 is a 0, what should the factor be? It should be x plus 1, right? It should be x plus 1. Okay, so from here, who can remind me what is the first step of long division? What do I want to do? Sorry? Yep.
Get the number on the top so that it's equal to, okay, it would be x squared, but it would be because that times the x in the front is equal to x cubed.
Exactly. We want to find the term such that if I multiply it with the leading term of my divisor, then I get the leading term of my, what the hell is the word for the thing that's under here? I can't, it's one of the other D words, but I can't remember it. Sorry? Yeah, dividend, yes. Right? No, I was thinking that dividend is on the top. That's the quotient. The quotient is on the top. Okay, well, anyways. See, even I get confused by this stuff sometimes. So, another way that you can try to find it, okay, is you can think, well, I need to find what I need to multiply this number by, or this thing by to get x cubed. Or you can just say, well, I'm going to take this thing and divide it by this thing. Right? X cubed divided by x gives us x squared. That will be the first term here. So now what I do is I just multiply it and subtract. So I get minus, I gotta use parentheses here, x cubed plus x squared. Why do I need the parentheses? Because I need to subtract both of these things, okay? So when I do that, hey, wouldn't you know, this cancels. It cancels because we made it so that it would cancel, right? And then we have 12x squared, and everything else just comes down. So we get plus 47x plus 35, yes? Okay, so now we just repeat this process. I take this thing and I divide it by this thing, and I get plus 12x. Okay, so now I get minus 12x squared plus 12x. Yes? And again, these cancel by design. And I'm left with 35x plus 35. So the last term is just plus 35. Yeah? Okay, so now that I've done that, I subtract 35x plus 35, and both of them cancel. So what am I left with underneath? 0. I knew that was going to happen from the start, because x plus 1 is a factor, which means that it can be divided evenly into the polynomial. By divided evenly, I mean I get no remainder, right? Okay, so now I have done all of this, and what is my gain? My gain is that I have learned that the function here, x cubed plus all this stuff, this function can be rewritten as x plus 1 times x squared plus 12x plus 35. Why is that useful? Because I'm trying to find out what numbers make this thing 0. And since this thing is equal to this thing, I can just figure out what things are going to make this quadratic 0, and then I'll have them all, right? So now I can just factor. We get x plus 1. Can this guy be factored? Yeah, what should I do if I don't know how to factor this one? Does that, if I don't know how to factor it, does that just mean that there's no more zeros? No, what do I need to do? If I can't factor a quadratic, how do I figure out the zeros? Plug in what? Yeah, you could plug in the other ones. Sorry?
It's like one of the theorems. I forgot what it's called. Quadratic formula. Yeah, quadratic.
That's the one. Quadratic formula, okay? Don't forget about the quadratic formula. You can always use that if you get stuck and you don't know how to factor something. But this one we can see, I think, is going to be x plus 7 and x plus 5, right? That's not that surprising. Okay, that's not that surprising. Why is it not that surprising? Because we knew that -7 and -5 were candidates for rational zeros, possible rational zeros. So at the end of the day, we got something which we could factor. So the set of all rational zeros is x equals 1, -1, -7, and -5. Okay, so all zeros in this case are real and rational. Okay? Real and rational. So this is how we use the rational roots test. It basically, the most useful thing that it does for us is it helps us to factor cubic or quartic or quintic polynomials, okay? We just use the rational roots test, we find a handful of rational roots, divide them out, and hey, we have just a quadratic. I know how to do quadratic. Okay, so are there any questions about that one? Forget who asked about that. Was that you, Rando?
Yeah,
Do you feel a bit better about this now?
it's way better.
Way better. Good. That's what I like to hear. Okay, well then maybe let's move on to something else. Does someone else have something that they'd like to discuss? Maybe a homework problem? Or you can just ask about a general topic. Yes?
Just like any of the ones from, I think it was 2.5, where like we had to graph them and then draw on, like I got the part up to the graph where like we had to figure out which way the lines were going.
Are you talking about rational functions
I think.
and rational inequalities?
Yes.
Okay, let's look at, maybe we can try to do a graph of a rational function, and then we'll do, okay, here we go. Use the 6-step procedure to graph the following function. Okay. So it's 2x plus 4 over x minus 2 and x plus 1 is f of x. Goal is to graph. Okay. So rational functions are kind of a pain to graph. But there's basically just a handful of things we need to consider, okay? We need to consider zeros, horizontal asymptotes, vertical asymptotes, and then also we need to consider behavior of each. So what do I mean by behavior? I mean, what does the graph generally look like nearby each of these things? Oh, and one other thing they want you to do is the y-intercept. That's right. I was like, there's something else, isn't there? The y-intercept is also something they want. Okay, so let's take a look at what this is going to look like. So let's start off with the zeros, okay? Where is this function going to be 0? What number could I plug into this function to make it 0? Well, this question seems scary when you look at this big rational function and you're like, oh God, how do I make it 0? Well, you're at the end of the day, when you plug in x, You're going to get a number on the top and you get a number on the bottom. If I have one number divided by another number and I get 0, then what can we say about these numbers? If I take one number divided by another number and I got 0, the numerator has to be 0, right? Something like 0 divided by 3, that's 0, right? Or 0 divided by any other number, right, would be 0. Okay, so what I want to do if I want to find the zeros is just take the top and set it equal to 0. So for the zeros, we just check when is 2x minus 4 equal to 0. 2x plus 4 equal to 0, sorry. So we get x equals to negative 2. Yeah? X equals to negative 2. And one thing that I do have to check here is I need to check whether that 0 is also a 0 of the denominator. But it's not, right? It's x equals to 2 is a 0 of the denominator. So we're not going to have a whole type of situation. So we have a 0 here at x equals negative 2. So here's 1 and 2. And here is where I'm going to put a 0, which means that the graph touches the x-axis. Okay, so that's the 0. Now to ask myself what is the behavior of the function going to be, well, I need to know, well, is my function coming down like this? Is it coming off like this? Is it going to go straight through? Like, what does the function look like at this 0? And the way I can tell that, okay, the way I can tell that is by taking, so we isolate this 0 in the numerator, basically. So we separate it out. So f of x, we rewrite it as like 1 over x minus 2, x plus 1, right? Multiplied with 2x minus 4, okay? So the behavior of the function near this 0 is going to be when I plug in the 0 into the rest of the function and use that as our prefactor. So if I do, so this is what we called like p of x over d of x or something like that. Okay, so what we get is the behavior near that 0 is going to be what we get when we do p of negative 2 over d of negative 2. If you multiply that with the function 2x minus 4, which is just a linear function, we're going to get the behavior of the function at that point. So what is that going to look like? 2x minus 4 is a linear term. So it's going to look like the function 2x minus 4. Sorry, plus 4. Jesus. Why did I do that? Okay. It's going to look like the function 2x plus 4. Or if this number is negative, it's going to look like the function like this, right? If I multiplied that function by a negative number, it would change the slope from positive to negative. So it's going to look like one of these two. But to evaluate which one it looks like, we have to check what is this number. Okay, so in this case, we get the top is just 1. So the top is 1. And then the bottom would be, what would I get if I plugged in negative 2? This would be negative 4 times negative 1. So we get 1/4 times 2x plus 4, which is x over 2 plus 1. So what does it look like? It looks like the function with slope 1/2. Okay, it looks like a function with slope 1/2 near here. Okay, so you're going to have to, okay, understanding this is a little bit tricky, and we went through it kind of quickly in class. But roughly speaking, for the behavior at a vertical asymptote, behavior at a 0, what do? We just take whatever that 0 is, whatever that x value is, and we plug it into what I'm going to call basically the leftovers of the function, okay? The parts of the function which aren't relevant for analyzing that particular 0, okay, is what I call the leftovers, all right? And the behavior of the function near that asymptote or near that 0 is going to be what we get when we take the ordinary behavior of that function, which is relevant for the 0, and multiply it with this prefactor. The prefactor is just what I get when I plug that 0 into what I'm calling the leftovers. Okay, are there any questions about how I figured out what the function looks like near that 0? All right, this is one of the more tricky parts of this class. So, you know, if you don't feel comfortable with this, don't feel bad. Just know that more practice is probably what you need in order to gain a mastery over this. Okay, so now let's do the next part. So the next part is we've got our zeros, right? So the next part is to figure out, do I have a horizontal asymptote or not? What do we think? Should I have a horizontal asymptote for this function? Maybe I can ask a more general question. When do I have a horizontal asymptote or not? What does that depend on? Anyone want to give that a shot? Yeah?
Depends on the power of the exponential functions on both sides.
Yeah, very good. It depends on the degree of the numerator versus the degree of the denominator, right? Because when we're talking about horizontal asymptotes, we're talking about plugging in extremely large values of x. If the degree of the top is like x squared and the degree of the bottom is x, then when x is extremely large, this number is going to get really, really big, right? But in this case, what do we have? We have the degree of the denominator is 2, and the degree of the numerator is 1, which means that the denominator, when x is really large, will outweigh the numerator. What does that tell us about a horizontal asymptote? If the denominator is getting huge and the numerator is staying comparatively small, what is that number becoming? If we take the denominator and make it really big, it means the number is getting really, really close to 0. Okay, so in this case, for the horizontal asymptote, we have degree of the denominator is bigger than the degree of the numerator, which tells us that y equals 0 is a horizontal asymptote. So that tells us that very far away, okay, we're going to get very close to, we're going to get very close to this line, right? Very, very far away. Okay? All right, so that's the horizontal asymptote. Let me leave the behavior for a little bit later. So next up, let's talk about the vertical asymptotes. When am I going to have a vertical asymptote? Hello, thank you. When am I going to have a vertical asymptote for my function? Yeah, Carter?
When the denominator is 0.
Yeah, when the denominator is 0. Very good. So if the denominator is 0, then we know the function's going to like blow up. It's going to do some crazy stuff at that point, right? So when is the denominator 0? It's 0 when x is equal to 2. So here's x equals to 2. And then it's also at x equals to -1. So we have two vertical asymptotes. So what we need to determine now is whether the function looks like, this. Okay, it could look like this maybe, something like that. Or it could look, something different. It could look like this. Something like that, okay? So what is the question here is, what is the behavior of the function as we march our x value closer and closer from each side of this, of these asymptotes, okay? So again, what is this going to have to do with? This is going to have to do with two things. First is the multiplicity m of these zeros, the multiplicity m, okay? If the multiplicity is even, we know we have same behavior on both sides. If the multiplicity is odd, we know we have different behavior on both sides, okay? Since the multiplicity of each of these is 1, we know we're going to have opposite behavior on each side of each of these vertical asymptotes. So we just need to figure out whether we're going down to minus infinity and then up, or if we're going up to plus infinity and then down on the other side, right? So the way we do that is, again, by looking at the leftovers. I need to check. So for behavior at x equals -1, we check what is the sign of the leftovers when I remove the 0. When I remove the 0, the leftovers are going to be what? The leftovers would be 2x plus 4 over x minus 2. If I plug in x equals -1, I get -2 plus 4 over -2 minus 2, which would be 2 over -2, which is -1, which is less than 0. So I check the sign of the leftovers when I am at this asymptote. So then I imagine, well, what is going to happen when I plug in a number which is very close to -1, but smaller than -1? So think about plugging in something like x equals -1.1. Then I know that the leftovers, f of x, will be close to whatever the sign of the leftovers is, times what? Times the remaining bit that we have. So that the leftovers takes care of this. So the remaining bit that I have is 1 over -1.1 plus 1. So what kind of number is this? This is a negative number. Yes? Negative number. So we take a negative number like -1, we multiply it with another negative number which is extremely large, right? So if I take a negative times a really big negative, I get a really big positive, which makes complete sense because we're going up at this 0. So it makes sense that we should probably connect it something like this. Okay, so now, do I need to check what I get when I plug in a number which is a little bit bigger than x equals -1? I actually don't. The reason is I know that the multiplicity of this 0, m, this multiplicity is 1. Yes?
When you did the -1 is greater than 0, you're supposed to, on the denominator, you're supposed to plug in -1, not -2. So make it 2 over -3.
Sorry, you mean here?
Yeah.
So what I did was I plugged in -1. So on the top I got -2. And then yes, this should have been thank you. This should have been -1. Which doesn't change the sign of this, right? I get -2/3, which is again less than 0. So the sign is still the same, which the sign is really the only thing we care about. We're trying to determine whether we blow up to positive infinity or blow up to negative infinity. So whether it's like using a factor of 2/3 doesn't really matter because we're going to infinity, right? Okay, so what does the function look like on the other side? We know that the multiplicity of the 0 in the denominator is 1, which is an odd number. That means we have opposite behavior on each side of this asymptote, which means I don't need to test a number which is close to -1 but bigger. I know that this function, I know that this function is going to look something like this on this side. Okay? All right, so now it's time to check x equals 2. Okay, we would use the exact same methodology, except I know for a fact that the behavior on the left side of this asymptote has to be like this. It cannot be like this. Does anyone know why I cannot have plus infinity behavior on the left side of this vertical asymptote? Yeah, very good. We know that there's only one 0. That's this one. If it passes through here like this, then it, by the intermediate value theorem, it must cross the x-axis. But we know that it doesn't, because we found all the spots where it crosses the x-axis. So I know that it cannot go up to infinity here. I know that it must turn around. And I know that since x equals 2 is a 0 of the denominator with multiplicity 1, there will be opposite behavior on both sides of this asymptote. So I know that this side looks like this. And finally, on the last bit, we know that as we pass through here, we briefly become negative. So in order for me to then go to the horizontal asymptote, I must go something like this, right? There's no way for me to do something like this. Why not? Because there's no zeros. There's no other zeros. We know we only have just the 1. So it has to approach from the bottom, okay? Same deal with up here. We know we're above the x-axis. We have to approach this horizontal asymptote from above on the right-hand side, because otherwise we would have to do what? We would have to cross the x-axis, right? And if we did that, we would have a 0 out here, but we don't have a 0. So at the end of the day, we've gotten the graph of this rational function. It comes down to zeros, horizontal asymptote, vertical asymptote, and y-intercept. The last thing I didn't write down is what is the exact y-intercept. The y-intercept is given by f of 0, right? Which is 4 over negative 2. Yes? 4 over negative 2, which would be negative 2. So that's exactly where our y-intercept is. Here's negative 1, and here is negative 2. Okay. Dare I ask, are there questions on this one? Yes?
So I'm just confused on how do you know exactly what direction it's going in? Like, where you say for the right side of the vertical asymptote, how do you know that's going to the right side down?
So how do we know what is the behavior of the function near an asymptote? Let me pull back up our notes because we had a good diagram for this. Here it is. Okay, so this was the behavior near a vertical asymptote. What did it say? Well, it said what we can do is we can take whatever that 0 is of the denominator. That's what we know is going to cause the vertical asymptote. We can break up our function as n of x divided by, we factor out that 0 from the denominator. And so we have this n of x over q of x is what I call our leftovers, right? And then we have the vertical asymptote part. So what we need to consider is two things to determine the behavior of the function near that asymptote. The parity of the multiplicity, so that means either even or odd multiplicity for that 0 in the denominator. So if it was like x minus 2 squared, that would be even. X minus 2 to the 5th, that would be odd. And then we check what is the sign when we plug in that number which makes this 0 into the leftovers, okay? So those were the two things that we checked. So when we checked those, we had this diagram of if m is even and the leftovers are positive, we have up, up. If m is even and the leftovers are negative, we have down, down. If m is odd and the leftovers are positive, then we have down, up. And if m is odd and the leftovers are negative, then we have up, down. So in terms of why this is true, you have to think a little bit more abstractly. So let's take a look at what happens when I take this function okay, and let's consider the asymptote at x equals 2 for now. So let's consider the asymptote at x equals 2 behavior. What I really want to understand is what is the limit of this function as x approaches 2 from above. Okay? As x approaches 2 from above. So what I mean by that is I'm going to plug in numbers like 2.1, 2.01, 2.001, ... right? This is what I want to understand is as the x value gets really, really close to 2, marching like so, yes, marching like so, is the function value going up, 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 up to infinity, or is it going down, 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 down to minus infinity? This is what I want to check. So if you think about it, the only thing that really matters is what is the sign of, we know that this thing is going to 0, right? Which is going to cause the going to plus or minus infinity. And whether it's plus infinity or minus infinity depends on what is the sign of the rest of it. Does that make sense? So what happens when I plug in 2.1? The top, okay, is going to be something like, oh, what am I doing? No. So 2 times 2.1 would be 4.2 plus 4 is 8.2. So something like 8.2. And then on the bottom, I'm going to have something like 0.1 times 3.1. Yes? So this is, you can tell, a positive number, right? And what's going to happen if I do 0.01, 0.001? Well, this number is going to get closer to 8. This number is going to get closer to 3. And this number is going to 0 from above. You see? So this is telling us that we're going to positive infinity, right? Why are we going to positive infinity? Because these things are like 8/3, right? And if I take 8/3 and I multiply that with something that's like going to infinity, then I'm getting positive infinity, right? Whereas what would happen if I approach from below? If I were to approach from below, I'd be plugging in numbers like 1.99, right? So this number would be really close to 8, this number would be really close to 3, and this number would be what? It'd be something like negative 0.01 or negative 0.001. So because the sign of this entire fraction is negative, and in absolute value it has to be going to infinity because we have something going to 0 in the denominator, right? So this is how we determine whether we're going up or going down. We know that we're blowing up. We just need to check what is the sign of that blow up. So that's the reasoning behind these diagrams, okay? So what I wanted to do here was cut out the work for you and say, look, you can do the limits if you want, or you can memorize this table, which tells you exactly what it's going to look like on each side of the vertical asymptote. Okay? Does that make sense? But loosely speaking, in a functional sense, most of the time you can fairly easily figure out what the behavior is on either side by plugging in a number really, really close to it, right? Because if you get something really big and positive, then it's probably going to positive infinity. If you get something really big and negative, it's probably going to negative infinity. So that's a way you can do it functionally, is just plug in something like negative 1.01 or negative 0.99, yeah? You can plug those in and you'll get a number which is either really big and positive or really big and negative, and you can do it that way. Does that answer your question?
Well, yeah.
Okay. Are there any other questions on this rational one? Okay, so one more thing I want to say about this is how would we solve this if this were like an inequality? What if we wanted to solve something like f of x is larger than 0? How would we do that? Well, to express the solution set, we have this nice graph here, and the graph shows us exactly where is f of x positive. What does it mean for the graph if f of x is positive? It means that the graph will be where? If f of x is positive, so f of x is the function height, right? If the function height is positive, then we're above the x-axis, right? So f of x positive, where are the locations that cause f of x to be positive? They're here and here, yes? So what would the solution set be? It would be something like -2, 1, union, sorry, not 1, -1, union 2, infinity, right? Something like that. So for rational functions where we turn them into a rational inequality, the only thing we need to check from if we have the graph already is just check where is the graph above the x-axis, right? Okay, well that took longer than I was expecting, but these guys really are a pain to try to graph them. So again, it's about the zeros, the horizontal asymptotes, the vertical asymptotes, and the y-intercepts. If you remember those things and you can kind of work your way through what is the behavior on each side of these things, then you can make a pretty convincing picture. Any further questions on the rational function? Yes?
Is there going to be a question like just like this on the test?
Is there going to be a question just like this on the test?
Please say no. Like,
What I'm saying is, look, there's going to be content on the exam that deals with rational functions.
but I'm talking about like the extent.
The extent.
Like, this took up like 2 pages.
You need to be able to know how to do the 6-step procedure to graph a rational function. Okay, that's all I'll say.
Multiple choice questions. Like, give me a hint.
Well, sorry? I mean, think about it this way. If you look at this problem, how long did this problem take us to do in class?
A long, long, long time.
Do you think you would have time to do this problem and 8 other problems?
No.
Do you think that I know that? Okay. I'm not saying that you're not going to have to graph a rational function. I'm just saying that this problem is a little involved for an exam, I think.
I feel like it would be okay if you gave us the graph and was like, can you take out these specific things?
Okay. Well, I'll think about that.
Okay, like, what's the vertical asymptote? Like, what's the horizontal asymptote?
Okay.
But couldn't we just literally look at the graph and be like, oh.
All right. Well, I'll take that into consideration. Thanks for your input.
You're so welcome.
Okay, what should we do next?
Go to bed.
Go to bed? Yes, Andrew?
The one that you said was definitely gonna be on the exam the other day.
Okay, we could do something from 3.1. Sure.
Looks like it passes through the different.
Let's see. Let's try something like that. Where is this problem? Here we go. We'll do 2. We'll do 2 of those types. The first type is the easy type.
Oh my god, bingo, I actually know how to do this.
Good.
That's good.
Nice. Everyone's gonna do it.
Passes through 0, 2, and 354. Okay, we're going to do an easy one and then a hard one. Let's start with the easy one. We have a function here which is an exponential function, and they tell us that these 2 points are on the graph. Okay, these 2 points are on the graph. Now, can someone tell me what is the relationship between an algebraic function and its graph. How do I get the graph of a function, period? This is 0, 2, 354, and a really bad comment. Yeah, I'm sorry. It's especially bad when I am trying to write fast.
No, I can read that.
Oh, okay. So what does it mean if a point is on the graph? So what would I do if I wanted to graph a function like x squared? How would I get the graph of f of x equals x squared? What would I do in order to graph it? Aside from the fact that I already know this is a parabola, how would I get the picture? If I wanted to sketch this, what would I do? I would take an x value, which are these numbers here, right? And what would I do? I would take that x value and I would plug it into the function. And then the point which I graph would be the point x comma f of x, right? Those are the points on the graph are the points x comma f of x, yes? So if I did 1, I'd get 1 squared is 1. If I did 2, I would get 2 squared is 4. If I did 3, I'd get 3 squared is 9, right? I take numbers and I plug them in. The height of the function is given by what I get when I plug in the x value. Okay? This is how we make a graph. So, if I know that 0, 2 is on the graph of the function, then what does that mean for this function? What does that mean for this expression if 0, 2 is on the graph? So the height of the function, yes, Griffin?
Let's see. I like to know the answer already in my head.
Yeah, but we want to know what it means.
Well,
So
0, that means A would be 1, so that C would be 2. Because if,
I don't think A is going to be 1, but
no, I mean, because if you put X for, like, if you put 0 for X, that would make A 1.
okay, I think we're on the right track here. 0 is going to go in for x.
You know what I'm saying? That makes
Right.
A 1.
So if we put in 0 for x, we get c times a to the 0, which is c times 1, which is equal to 2. So it's a very simple procedure here. If 0, 2 is on the graph of this function, then that means that when I plug in 0, I get 2. Okay? When I plug in 0, I get 2. Because the height of the function is given by what I get when I take that x value and I plug it in for x. Right?
Well, I know much easier to do this.
Sorry?
The way that I did this was very different.
Okay.
I just automatically paired the two, and then I just
Can you describe what you mean?
It'd be easier if can I just show you?
Yeah, sure, bring it up. So in this case, what does this tell us? This tells us that c is equal to 2, right? So now I can update my function. I know my function is going to be something like 2 times a to the x.
Yeah, like I just automatically put it.
Yeah, so f of 0, you replaced by 2, right? So the only difference of mine is instead of replacing it underneath, I replaced it to the side.
Okay.
You see what I mean?
Yeah, sorry, it doesn't look like mine. I was really
Yeah.
confused.
Yeah, it's the same. Okay, so now we know that this is true. So now we can use the other point. I also know that 3 comma 54 is on the graph. If 3 comma 54 is on the graph, then that means if I plug in 3 into this function, I'm gonna get 54 as the answer, which tells me what? F of 3, what would that be? That would be 2 times a cubed is equal to 54. Okay? I think it's very important to have a grasp on what is the graph of a function. It's just a representation of the inputs and outputs, right? we put the inputs on the x-axis, and we put the outputs on the y-axis, right? And then we just say, well, I'm going to take whatever the input is, I'm going to plug it into the function, and the height of the function is just going to be the output, right? So you can use this in reverse. If I know what is the height of the function for a given input, then I know what is the value of that function when I plug that input in, right? So it's a two-way relationship, right? So f of 3, if I plug 3 into the function, I know the height should be 54, which means if I plug in 3, I get 54. If I plug in 3 to the function, I get 2 times a cubed, and we can solve this. What does this mean? A cubed is going to be equal to, what, 27? A cubed is going to be 27. So what should a be? We want a number such that if I do a times a times a, I get 27. If I do 9 times 9 times 9, I think I'm going to get 729 or something like that. I think it should be 3 times 3 times 3, yes? That would give me 9 times 3, which is 27. So a is 3. So now, altogether, the function will be what? 2 times 3 to the x. Yes? Okay, so why do I say this is an easy one? This is an easy one because, well, it's not necessarily because it's easy. It's just easy in comparison to the next one we're going to do, which will be harder. The reason this one is a little bit easy is because when we plugged in 0, what happened? The a just basically went away, right? When we plugged in 0, a to the 0 is 1, and so we got c for free. We didn't have to do any more work to get c. So let's see one where it's a little bit more complicated than that. So let's see one where we have f of x, again, is equal to c times a to the x, and we have it passing through the points 1, 1, and the point 2, 8. So this is a different type of problem, which is a bit harder. Okay, so why is it harder? It's harder because this number isn't 0. If this number was 0, we would be able to get c really fast. So let's use the same exact procedure for this one, okay? I know that if I plug in 1, the answer is 1. So what does that tell me? That tells me f of 1 is c times a to the 1 is 1. And also, f of 2 is what? C times a squared. And that is equal to 8. So why is this harder? This is harder because I don't just immediately figure out what c is, do I? There's still an a here, right? There's still c times a is equal to 1, and then the other one says c times a squared is equal to 8. So am I doomed, or is there something I can do? Doomed. No, we wouldn't give up that easily, would we? Okay, so there's two ways I can proceed from here. I'll show you both ways. Way 1 and then way 2. And you can decide which one you like better. Way 1 is to take these two equations and divide them by one another. If I have c times a is 1 and ca squared is 8, then ca squared over ca is going to be what? Ca squared is 8, right? And what is ca? 1. So if I replace the numerator by what it's equal to, I get 8. If I replace the denominator by what it's equal to, I get 1. Says who? Says these two equations. Well, the reason that I'm dividing them is because what's going to now happen here on the left side? Ca squared over ca. What happens with the c's? They cancel, right? And I get a is equal to 8, because a squared divided by a is a, yeah? So that told me that a is 8, so how do we proceed from there? We know that c times a is 1. And we know that a is 8, so c times 8 is 1. So therefore, c is equal to what? 1/8. So therefore, f of x equals 1/8 times 8 to the x. Okay, so way 1, I find some students find this a little bit unintuitive, like you're saying, okay, to take these two equations and divide them. But what am I doing? I'm just saying, well, I have two numbers. There's no reason I can't divide those numbers, right? I can do CA squared divided by CA. And I know that CA squared is 8, so I replace it by 8. And I know that CA is 1, so I replace it by 1. Yep. Okay, and then it cancels the C's. Okay, so that takes a little bit of foresight. What if I don't have that foresight? Well, you can use way number 2, which is just to solve this using substitution. We can take CA equals 1 and say, well, therefore, I'm going to isolate C. C is equal to 1 over A. Okay? Then plug into the second equation. Plug into the second equation. So then we would get what? We're going to say CA squared is equal to 8, but I'm going to replace C by 1 over A. So I would get 1 over A times A squared is equal to 8. And that would tell me what? That A is equal to 8. Then I again go back and plug in to the other equation, and I get C times 8 is equal to 1, and so therefore C is equal to 1 over 8. And therefore f of x is equal to 1 over 8 times 8 to the x. So way 2 is a little bit different. What do? We isolate one of the variables and replace it in the other equation. This is called substitution. Okay, what do we think? Who likes way 1 the best? Who likes way 2 the best? Okay, I'm surprised. More of you like way 1. I would think that maybe more of you like way 2, but okay. I mean, either way you want to use is totally fine. I'm not going to be picky about it as long as you are able to use correct reasoning and show your work and arrive at the correct answer. So hopefully you get a sense of why this one is a little bit harder than the other one, right? When we do this one, we get C right away for free, right? Because we plug in 0 for x, so the A just goes away in this equation, and we get C. In the other one, we get two equations which both have C and both have A. So to solve it, we need to either divide them by one another in order to cancel the C, or we need to use substitution to replace one by the other. Okay, so that's that problem. Are there any questions on this exponential through 2 points process? Okay, then we probably got time to do one more problem here. Does anybody have one that they want to do? Hang on, I'm going to let somebody else ask if they have it. Anyone else? Okay, then Randall.
How do you do the intermediate value theorem?
Sure. How do you do the intermediate value theorem? Well, the intermediate value theorem will help us answer questions like this. Okay, so let's think about it. If we did x plus 1 and x plus 2, we'd get x squared plus 3x plus 2. Let's take this equation and say it has a 0 between 3 halves and 5 halves. Has a 0 between 3 halves and 5 halves. So we want to show that this function has a 0 in a given interval using the intermediate value theorem. Okay. show that this function f of x has a 0 between 3 halves and 5 halves using the intermediate value theorem. I want negative 3 halves and negative 5 halves, don't I? Yes, I do. Okay, so how do we do this? Well, the intermediate value theorem says basically the following. If my function is continuous, and at one point it's below the x-axis, and at another point it's above the x-axis, then what had to have happened in between? We must have crossed the x-axis. It's a very simple, intuitive type of thing. It's like if I was flying at 10,000 feet, and then later I was flying at 30,000 feet, then at some time in between I was probably flying at 20,000 feet, right? So this is the intermediate value theorem. So all we have to do is check what is f of negative 3 halves, right? So we plug it in. We get 9/4 plus 9 halves. No, minus 9 halves, sorry. Minus 9 halves and then plus 2. Okay, which is 9 minus 18 plus 4 all over 2, which is, let's see, the negative 9 plus 4 is negative 5 halves, which is less than 0. Then what do we get when we do 5 halves? Negative 5 halves. When we do negative 5 halves, we get 25 over 4 minus 15 over 2, and then plus 2. So this is 25 minus 30. Have I done this right? 25 minus 30, and then plus 4, right? Sorry? Oh, thank you. Yes, plus 8. Jesus. All over 4. So this is 3/4, which is positive. Okay, so what did we say? We say that basically when we plug in negative 5 halves, we get something positive. And when we plug in something like negative 3 halves, we get something negative. So because f is continuous due to its polynomial, by intermediate value theorem, it must have a 0 between negative 5 halves and negative 3 halves. Okay, sorry, I probably went not over. So this is the intermediate value theorem. We just need to, if we want to show that the function has a 0 in a given interval, we check the value of the function on each side. If the function changes sign, it must pass through the x-axis. Right? If the function changes sign, it must pass through the x-axis. Okay, that's it for today. Don't forget I have office hours today from 2:30 to 4. I'll see you all there. And I'll send an email about where it's going to be.